Good afternoon. Again, I'd like to thank the organizers for such a wonderful meeting. It was my first time in Taipei, and I really like the city. It's very warm environment and warm people. It's a pleasure to be here. So I will basically continue what I have started last time in Shanghai, but I understand that some people were not during my talk in Shanghai, so I will just define the setup and try not to use too much what has been done in the previous time. So the setup is the following. So we consider CFT, conformal field theory in vacuum state. And as usual, we would like to explore Rayleigh entropy or entanglement entropy of spatial region. So we have some region. So this is E equals, say, constant slice. We take some subregion A, we trace out the complement of A, and define the density matrix. So the density matrix, reduced density matrix of A is given by tracing out the degree of freedom associated with the complement of A over the pure state. And by definition, this is just exponent of the so-called modular Hamiltonian. And during this talk, I would like to present you some details of the structure of the modular Hamiltonian, because in general, as you know, it's a very complicated operator. It is non-local. We know this modular Hamiltonian, say in flat space for CFT, we know it only in one case, basically, sphere. Well, and plane is the limit of the sphere. Of course, by construction, there is nothing inside, there is nothing but geometry in this density matrix, because CFT has no scales. We consider vacuum state, so there is nothing but just geometry and some numbers that define a particular CFT. Therefore, entanglement entropy, or more generally, Rayleigh entropy, which is by definition is 1 over 1 minus n log raised of rho to power n, has only pure geometric structure, say in 4D. So it's pure geometric. So say in 4D, we have the following structure. So Sn equals, so it has some constant times area law over epsilon to power 2, epsilon square. Okay, this is the standard area law. Epsilon is UV cutoff, because as we know, in quantum field theory, entropy diverges. Then there is subleading logarithmic divergence. So the conventional way to write it is FA n over 2 pi times integral over the entangling surface. So sigma denotes the entangling surface that separates A from the complement of A. So this is intrinsic curvature of the surface. Then there is another constant that depends on n over 2 pi. So here we have k tilde ij, so this and sum over A. So k tilde is extrinsic curvature of the surface. Surface is 4 dimension 2, so we have 2 extrinsic curvatures. So index A runs over 1 and 2. Indices ij are parallel to the surface. And k tilde is just the traceless part of the extrinsic curvature. So k tilde ij is simply the standard extrinsic curvature. For those who is not used to work with extrinsic curvature, this is just covariant derivative of okay, write it this way. D mu I, D mu J. So this is the definition of the extrinsic normal vector to the surface, you expand it into the bulk, to the vector field in the vicinity of the surface. You take a covariant derivative of this normal vector and project it onto the surface. So K tilde is just the traceless part of the characteristic of the extrinsic curvature. And there is an extra term that is associated with the background curvature. So again, it's integral over the sigma. Then we have gamma ij, gamma kl, c I k j l. So this is wild. And so this guy is multiplied. Okay, let me continue here. So this is a law of, so it's a logarithmically divergent piece, L over epsilon, where L is characteristic scale of your geometry. And then you have some constant, another constant, so let me call it constant 2, and this is constant 1. So it's all the same constants. So it's a pure geometric object, numbers, and some geometry. So the question that we raised last time is the following. Is there a simple geometric expansion of H, of this H that defines this radiant entropy, that enables to recover the above structure. Okay, simple geometric expansion of H. So I remind you that in principle the most interesting part of the structure is the logarithmic piece, because other pieces are non-universal. That means that by changing your cutoff or changing your lattice if you wish, you may change these constants, constant 1 and constant 2. The standard explanation is that if you just rescale your epsilon if you just take your epsilon and send it to some alpha time epsilon, then the constant 1 changes by alpha 1 over alpha square, and constant 2 gets this logarithmic shift because you just get the same piece times log of alpha. So both constants, constant 1 and constant 2, are changing under scaling of your cutoff, under changing of your lattice a little bit, while the logarithmic divergence does not change. That means if you could in principle measure this quantity, all experimentalists will agree about the logarithmic divergence, but will disagree about the area law and this constant, because everyone will use his own favorite method of regularizing things. So last time we already mentioned that to recover this piece, so I will just reformulate it, paraphrase it a little bit differently, what I have said last time. So we observe. Last time that a sigma piece turn, area turn, is fully recovered by taking the following approximation. You take your full modular Hamiltonian and approximate it by Richter modular Hamiltonian, which is minus 2 pi integral of T mu. Okay, let me write it this way. So integral over A. And yeah, I'll write it explicitly. Sigma. So it's two-dimensional surface. X times X. E 0, 0. Then there are corrections that I will discuss in a moment. So this piece, this is the so-called Richter Hamiltonian. In Euclidean geometry, it generates rotations around the plane. Okay, so if you consider just plane, because if you want to consider this constant for some reason, then you may say, okay, let us take, it's a constant, it is independent of any geometry, just number. So let us take a very special surface, just plane in flat space. So for a plane in flat space, this piece vanishes, this cosine vanishes, extrinsic curvatures vanish, because, well, plane is flat, and in flat space, and this curve vanishes because the plane has no intrinsic curvature. So you're left only with this piece, and to get this number, the claim is that this is what you need, because in this case, if this is your plane, then so by just the setup is symmetric with respect to all two rotations in the transverse space to the plane. So this is Euclidean time, and this is orthogonal direction to the plane. So there is a symmetry. The state is also symmetric. Vacuum state is symmetric under all two rotations, and therefore your modular Hamiltonian is simply generator of rotations in this transverse space. And what is written here is just generator of rotations. In Lorentzian picture, it becomes boost in the x t plane. Okay, so this is what it is. Or in other words, you can say that that area law equivalently, area law is recovered from the leading singularity in this correlate, in the one-point function. Okay? In T mu nu n. Why I'm saying that for the following reason. So if this is your surface, and you introduce here insertion of T mu nu, and the insertion is very close. Okay, close means that the distance, let me denote it by r, over characteristic scale of the curvature is much less than 1. Okay, then to leading order, to zeroth order in r over L, where L is just the curvature of the surface, this operator thinks the surface is flat. Okay? And for a flat surface, you know how to write down this correlator. Actually, this one-point function, because how it looks like. So the T mu nu, well, you have to split indices into parallel indices, mixed indices, and orthogonal indices. Then here, well, because of rotational symmetry, you just take the limit when you now expand this correlator in powers of r over L. So to leading order, you just think L infinity. So L infinity means flat plane, and then this leading order singularity is just given by, you reconstruct it by symmetry argument. So the Tij can be proportional just to delta ij over some power, and the power is 4. We are in 4 dimensions, so it's 4. Well, in d dimensions it will be d, but let us write it in 4 dimensions. And then there is some coefficient here. So conventionally, we take this coefficient. People who get this coefficient will be equal. So this minus hn over 2 by n delta ij over r to power d plus some terms of order r over L. Now this guy vanishes, so and then plus terms of order r over L. And this guy, there are two structures that you can write down, and they are completely fixed by requiring conservation and tracelessness of the stress tensor. So this is something that I, Janet, and Rob Myers analyzed a while ago, and so this Hn has the name of conformal weight of the twist operator of your deformation here, and the final expression that you can get again very simple. You just write down all possible structures and impose conservation, as I said, for and A and B and C. C, I will explain now the notation, R to power 4. So NA, so if you think if your stress tensor is inserted here, this is mu x. So NA is just a unit vector that points in the direction of insertion. And these numbers, so up to overall number, so in general there are 3 structures, 1, 2, and 3. And then you have 2 constraints, so that means that 2 numbers out of 3 are fixed, and the only number that is not fixed is this Hn. So the Hn is called, as I said, conformal weight of the twist operator that sits on the surface, and in the paper that I have mentioned, we analyzed how it is related to energy in the hyperbolic space. I will not discuss at this point here. So this is what you get to leading order. Why it is related to this Hamiltonian? For the following reason: if you take derivative with respect to n of this object, just differentiate it with respect to n, then on the left hand side and set n to 1. Then on the left hand side you will get correlator of the stress tensor with the modular Hamiltonian. Why it is true? Because you can write this correlator in the following way. So it's just vacuum expectation value of Eijx times e to power minus n minus 1 h vacuum. So this is identity here. Okay. Is it clear? Because again, if we are talking about replicated manifold, T sits on one of the replicas. The rest of the replicas are empty, but each empty replica corresponds to 1 power of rho, of density matrix, rho. So and rho is e to power h. So therefore you have n minus 1 replicas empty, so this is what you have. And where T sits is just a vacuum, because your rho is just trace over of the vacuum state. Okay. So and now it is obvious that if you differentiate it with respect to n and set n to 1, you get correlator of T with h. On the right hand side, you get just derivative of h. Well, you could differentiate n, but recall that if n is 1, then this correlator becomes just vacuum expectation value of the stress tensor, and it vanishes. So you have to differentiate, h vanishes as n goes to 1, so you have to differentiate h, and that means that on the right hand side you get something nice that knows nothing about curvatures. On the left hand side you have just correlator of Tij with h. So out of here is full h. But to get just this piece, this leading singularity, you do not need full h. You need only very concrete part of it, which is given by taking L to infinity. But as you take L to infinity, it means that your surface becomes straight. And for straight surface, for planar surface, h is just hr. So think about h as some operator that is a function of your geometry. So to recover this piece that is independent of the geometry, you can just send your curvatures to L to infinity. And in that case, h becomes simplified and becomes just linear, just this Hamiltonian. And that means that leading order singularity, this is all you need to know about h. That this is just a linear, very simple expression. The question now is, of course, how to get correction, R over L, linear correction in this small parameter, R over L. Okay, this is what I'm going to tell you, but in principle, the recipe is written here already. So what you do, first of all, you have to calculate these correlators next to leading order. You have to calculate. And secondly, you have to write all possible corrections that are linear in R over L, where R is the insertion of the stress tensor. So you write down here corrections proportional to 1 power to inverse power of L, which it means that correction is proportional to the extrinsic curvature. Here you calculate linear order corrections in R over L. Then we differentiate with respect to n both sides. So here on the left hand set n to 1. So on the left hand side you will get correlators of t with full h. On the right hand side you will get something, well, some known known expression because you explicitly calculate it. And then you require that they match. In which case you completely define the coefficients of unknown terms that we will write down now. Is it clear? Okay. So again, so the idea is very simple. If t is very close to the surface, then to leading order, it just the only part of the modular Hamiltonian that matters is the Rindler part. And then, as you increase your accuracy, you have to account all consistently corrections in the curvatures in 1 over L. So this is what we also call derivative expansion of your object of the modular Hamiltonian. So the question is, of course, how to calculate these curves. So one approach that organizers of this conference undertook is to write down again all possible terms that are linear in R over L, proportional to curvatures, and impose conservation, tracelessness, and conservation of the stress tensor, standard conservation. So I have to write down the names. So there are 3 names. So in 3D. So I think it's scene 1. So they were not interested too much about the structure of the modular Hamiltonian. They were mostly interested in the structure of this one-point function, or if you wish, sort of OPE expansion when t approaches the approaches the twist operator that sits on the surface sigma. So what they did, they wrote down all possible terms, all possible corrections, and required conservation of the stress tensor and tracelessness. And this way they got all kinds of constraints. So we will not follow this route, it will be a little bit different. So in 3D, one can write down all possible scroll down all possible terms, all possible corrections up to O R over L squared, and imposed constraints based on mu equals 0. So based on these 2 requirements. Okay, so we will not do it. Let me postpone for a while the discussion of what kind of calculation we can use to find these structures. Instead, let us just write down. Let us consider what kind of terms we have here. So in general, at O R over L order, are two structures that are relevant. There are two relevant structures. One is just trace of the extrinsic curvature, and the other one is what we call K tilde ij. So if you are interested, for instance, in these corrections, then in principle you can write a bunch of terms. So, possible terms. So delta H, therefore, so delta H, the correction to this part, you can write all kinds of terms. So, for instance, you can write something like that. In principle, all possible terms you should write down. So this is A. A means this area. Or, well, I provided explicitly. So E minus 2y, Ex. So you could write something like that. Ky squared, E not. This is just trace of K. Defined as K without indices. You could write a term of this form. So it's E minus 2y, Ex, Kx squared, E not. You could write term to this form. So y, Ex, yi, yj, Eij times K. And you might continue. So before I write down possible terms for this guy, let us just fix the coefficient here because this is extremely simple due to the work by Cassini, Huerta, and Myers. So Cassini, Huerta, and Myers found how the modular Hamiltonian looks like for a CFT and for an ideal sphere. So sphere, what is nice about it, that sphere has a non-zero curvature, trace of the extrinsic curvature, but this piece, the traceless part vanishes for a sphere. So that means you add all these corrections here on the right hand side, but the numbers you still do not know. So to fix these numbers, you can just look at the spherical case, and the spherical case will completely define these numbers. Okay. So what we use here is the fact that if you are very close to the surface, it looks like flat. Now, if you increase your accuracy, then you start to distinguish, see this curvature, and say if you're in 3 dimensions. In 3 dimensions there is no traceless part because it's just 1 by 1 tensor. So in 3 dimensions there is only trace K, and say in 3 dimensions you would not be able to order R over L distinguish your surface from circle. It will look like circle this order. And therefore circle completely fixes these numbers. In particular, based on Cassini, Huerta, Myers result that states that the modular Hamiltonian for a sphere is given by 2 pi integral over the ball of r squared minus r squared over 2r times T naught naught, K plus maybe constant, normalization constant. So you can use just this result to recover these coefficients here in the following way. So if you think about your sphere, so this is x, this is y, here is your sphere, this is the center of the sphere. So the integral is over ball over this region. So this is ball of radius r. So integral is over the interior of the sphere. So of course this is just integral d minus 2y dx over this region. And here you write down